Today, I will go through some practical examples of machine learning in Python. I recommend you to use these textbooks as a supplementary material to the following Jupyter notebooks. So let's recap what is machine learning. There are different definitions of the machine learning, right? So one of them is, as described here, machine learning is a process of extracting knowledge from data automatically and then using that knowledge for making prediction on new data, unseen data example. Classical application of machine learning is in spam filtering. For example, given a bunch of spam and non-spam emails, machine learning algorithm can learn automatically to identify whether a future email contains spam or non-spam email contents. In other words, machine learning algorithm allows us to learn a model, a predictive model from the data for different applications, whether for spam filtering or for credit card approval, or given data from X-ray images, for example, we can train a machine learning model to identify whether those X-ray contain lung cancer related patterns or not. The central to machine learning is a concept of automating decision making from data without the user specifying explicit rules. The second central concept is generalization. The goal of a machine learning model is to predict new, previously unseen data as accurately as possible. Okay, this is very important. For example, in real world application, we are more interested in making prediction on future samples, future emails examples, whether it contains spam or non-spam content, right? For example, if we consider these two training data and with labels as bunch of email containing spam, non-spam, we train a model based on this training data. So generalization is whether our model can generalize the knowledge extracted from training data to unseen test data. Okay, according to some metric, whether this can be accuracy, error, or cost. Okay, this is evaluation. Okay, if the test labels are available, we can evaluate the performance of the model's generalization on test data. Here, the data can be any quantifiable discrete data, images, sounds, text data, or any other type of data. Okay, so and data is presented to the algorithm, to the model, using a two-dimensional array or matrix of numbers, or sometimes n-dimensional array, right? And each data point, we also know it as a sample or training instance that we want either to learn from or make a decision on, is represented as a list of numbers. And those numbers are called as feature vectors. And its containing features represent the properties of this point. For example, this is one of the very popular dataset that has been collected in early 1930s. So here it's called as iris dataset that has the measurement of 150 iris flowers, okay, that belong to three different species: Iris setosa, Iris versicolor, and Iris virginica. This is also, I can say, is kind of hello world dataset for machine learning, simple machine learning algorithms. Okay, so the task here is given three different type of data. We will see later. Want to learn a model to classify, automatically recognize a new image of data, for example, with some measurements, whether it belongs to Iris setosa, Iris versicolor, Iris virginica. Now the question is, how can we represent these flowers as our data? Okay, one way is represent each flower sample as one row in our array, two-dimensional array, for example, and columns, features. Columns represent the features, which is the measurements in centimeters. Okay, for instance, this is the features or the attributes, and here each row corresponds to each separate flower, 150. Okay, first flower, second flower, third, and up to 150. And each flower has four different measurements. Okay, measurements of the length and then width of this petal and sepal Supervised learning is one type of the machine learning tasks, which can be used for classification and regression. In supervised learning, we have a dataset plus the desired output. Okay, and dataset contains some attributes, input features. It can be a bunch of spam, non-spam related examples where we have the labels corresponding to them, which one is spam, which one is not spam. And then the task in supervised learning is to construct a predictive model based on the data, which we can use later for predicting the correct output of an example outside the dataset, which hasn't been seen by the model. And we have some other examples of the classification or supervised learning tasks. For example, given a multicolor image of an object through telescope, this is your data. The task is to determine whether that object is a star, quasar, or galaxy. This is a supervised learning task. Okay, it's a classification task. Another example is given a photograph of a person represented as image data. Your predictive model will identify the person in the photo, okay, in your model that has been learned using other images of this person. Given a list of movies, a person that has watched it represents a dataset. We train a predictive model that includes a personal rating of a movie. The task would be take a model so that it will recommend a list of movies the person would like. Okay, if in Netflix you see this algorithm working, so movie recommendation. Given, for example, a person's age, education, and position as a set of data set, your task is you train a model, okay, and infer their salary. What all these has in common is that there is one or more unknown quantities associated with the object which needs to be determined from other observed quantities. We can further separate supervised learning into classification and regression. In classification, the label is discrete. In regression, the label is continuous. So discrete can be binary, yes and no, plus or minus one, for example, spam or not spam. Okay, and it provides clear-cut distinction between different categories. While in regression, the label or expected target is continuous. It's a real valid output. For example, in astronomy, the task of determining whether an object is star, galaxy, or quasar is a classification task. The label is from three distinct categories. On the other hand, if you wish to estimate the age of an object based on such observation, this would be a regression problem because the age is a continuous quantity. It can be 100 years, 1,000 years, or just 2 years, right? So in supervised learning, we always have a data set and then label. Let's now recall the unsupervised learning. In unsupervised learning, as you know, there is no label, no desired output associated with the data. Instead, we are interested in extracting some form of knowledge or model from the given data. So we can think of unsupervised learning as a means of discovering labels from the data itself. All right? And we know that unsupervised learning is considered one of the hard problems in machine learning. And unsupervised learning consists or comprises the tasks such as dimensionality reduction, clustering, finding the grouping of the given data, or density estimation. We have reviewed all this in our second lecture, right, in types of learning. So in the case of iris data, discussed above, we can use supervised method to determine combination of measurements, okay, combination of features, which best display the structure of the data. Okay, as well, we will see later, such a projection of the data can be used to visualize the four-dimensional data in 2 dimensions, right? Some other examples of supervised learning as follows, given, for example, detailed observation of distant galaxies. Our task is to determine which features or combination of features summarize the best information. Here we have only data, no label at all. And we need to use the clustering tools to find the best combination of features. Or he given a mixture of two sounds. Okay, for example, a person talking over the music. Then we can use clustering to separate two sounds. We can separate the person and then the background music. This kind of problem is called blind source separation problem. Another example, given a video, our task is to isolate a moving object, this is data, and categorize in relation to other moving objects which has been seen, right? Or given a large collection of news articles, we need to categorize these articles into different topics, or find recurring topics inside these articles. Given a collection of images, cluster, group similar images together, okay, without using the labels. Just use some similarity, some other metrics within the unsupervised learning. Okay, group them to when visualizing the collection. Now we can summarize the taxonomy of machine learning. So generally, machine learning is divided into unsupervised, supervised learning, and we also have semi-supervised learning we didn't discuss here. In unsupervised learning, we're interested in performing clustering, given data without labels, or dimensionality reduction, which mainly focus on reducing the dimensionality or the input feature of the data, or an anomaly detection, detecting some data with unusual distribution as compared to the remaining dataset. In supervised, we have regression problem. We have y labels. In the regression case, y can be any real valid number. In classification, we have y's, usually in the form of discrete numbers. We also have a ranking, which can be also classified as supervised learning. Manipulating Numpy arrays is an important part of doing machine learning or any type of scientific computation in Python. Numpy is a Python library which we can use for working with arrays, n-dimensional arrays. The Numpy has functions for working in the domain of linear algebra, Fourier transform, or any matrices. Okay? It's an open source project which we can use freely. And Numpy stands for numerical Python. So let me open the console for this Jupyter notebook. And then you can find some more details of NumPy in the documentation. So if you just type np question, we see that okay, NumPy provides an array object of arbitrary homogeneous items, also provides fast mathematical operations over arrays, linear algebra, Fourier transforms, random number generation. Okay, so you can go to online for documentation if you want to find more details, or this library also provides some documentation. For example, we can try to explore what kind of operations the library has. So if you just scroll down and up, you see some LG, linear algebra, some related operations, and also you see max. Probably this will find the maximum, just guess, and many other operations that we can use. So these are trigonometric functions, right? Arc cosinus, arc max, arc mean. For example, if you want to find out what does this arc mean to, we just do this, right? This is one of the useful function, allows us to find the minimum of values of the indices along the provided axis. If you pass some NumPy array A to this function and use this method, it will give you the minimum of that array in the defined axis. Many others. So just study yourself, explore it, and we can use, for example, operations such as matrix inversion, which we mentioned in linear regression problem, right? Also, matrix multiplication. That is a basic operation that uses perceptron. Or, let's say, logistic regression also. You can use NumPy to implement those operations. Why NumPy? NumPy provides us very fast C-level speed in performing those operations, mathematical operations, in Python environment, right? Python itself is very slow. So NumPy is one of the main C-based library, C++ based library available for us doing machine learning, Let me show you very simple examples of how we can use NumPy, okay, in this notebook, but you can explore more yourself. So let's first import NumPy as NP. NP stands for NumPy. It's actually the convention many people use. You can call it whatever, however you want. And this is random number generator. You need to set as seed of this random state for reproducibility. So if you are curious about what this does, is again, look for the question, right? So you can find the documentation here. So container for slow Mersenne twister pseudo-random generator. So consider using different bit generator and with the generator container instead. So random state exposes a number of methods for generating random numbers drawn from a variety of probability distributions. So we can use this seed as here and then generate a random array according to uniform distribution with those parameters, low and highest values, and size of the array, 3 by 5, okay? And then we can see this is our data. I can open the variable explorer as well. So this is the data we generated, x 3 by 5. Now, yeah, NumPy array also uses zero indexing, just like other structures in Python. So if you want to access this element, you use 0 by 0. Okay, so let's see. Indexing. All right. So you call you indicate the row and column index, and you get this. What does 1 do here? All right. So 1 gives us the following entire row, second row, 0th row first, and then second row, right? How about this? This will give us the column, okay? This column. Well, anyway, just these are very, very simple examples. You can just check yourself. The other operation we commonly use is matrix transposing. It's as simple as doing, okay, given x dot t. Okay, that will give us a transposed matrix. So original matrix, which is 3 by 5, if we transpose it, which will be given by 5 by 3, right? This matrix has been transposed as the following, right? So we can also look for the type of the x. X says it's and the array. And just to find out what you can do with this array, all right, just type the dir and then you see flatten product, okay, and sort standard deviation, convert to list, to file to list, here transpose, okay, variance, calculate the variance. So these are all the methods, okay, attached to this Python object, an NumPy object. Okay, we are dealing with this object. Each object has the methods. So we can also do this transpose, which will perform the same thing. Just explore yourself. So what was flatten? Okay, returns a copy of array collapsed into one dimension. Returns one-dimensional vector. Look, this flattens this into one tall dimensional vector. Well, anyway, just explore yourself. Okay, now let's see some more examples. So create a row vector of evenly spaced numbers over a specified interval. So lean space function allows you to create. Okay, so you need to provide 0 beginning and end and the maximum number. We can turn the row vector into a column and vector by introducing this numpy new axis. Right? So this column will be turned into, this row will be turned into column vector. Well, one of your homeworks, you are asked to generate sample data, right? Probably you have used already NumPy's data generator. So NumPy library also allows us to perform fancy index. For example, given the following array of 3 by 5 dimensionality, we can define to select subset of this matrix. How can we do that? For example, I want to select 0, 1, 2, 3, right? So third column, first column, and then zeros column. Select and rearrange, right? We can do that as follows. So you just define which column, okay, and pass to your array. Or you can also select subset of this matrix in row wise, okay, along row axis. There is another library called Scipy. Okay, Scipy is a scientific computation library that uses NumPy underneath. It is built on top of NumPy. Okay, and it stands for scientific Python. This library provides more utility functions. For example, the optimization or statistics and signal processing functions. Like NumPy, Scipy is also open source. That means we can use it freely. So let's try to take a look at what kind of methods the Scipy library provides. Okay, so we imported Scipy, and then so doing Scipy probably gives some quick overview of what kind of methods it provides. You see, base to log, base 10 log, for example. Just take a look. So one of the useful tool of Scipy is in creating sparse matrices. For example, we see that in most applications, okay, sparse matrices are very important. In some machine learning tasks, for example, especially as those associated with textual data analysis, most of the data may be zero. Okay, when you encode text in by numeric data, the resulted array may be mostly zero. And storing all those zeros is very inefficient. And representing in a way that only contains the non-zero values can be much more efficient in terms of memory. Okay, we can create and manipulate sparse matrices as follows. Let us first create a random matrix sampled uniformly, okay, was the following size, 10 by 5 array. And then from this, we create another matrix by making most of the entries zero. We are creating a so-called matrix with a lot of zeros. Okay, we assign the values below 0.7 to 0. And here we can see that storing most of these zeros can be computationally demanding. Okay, here we have simple matrix, but in real world application, we're talking about the matrix with thousands of dimensionality. Okay, now we can use the Scipy's sparse method to convert this most zero array into sparse form. We pass it to sparse, okay, CSR matrix. Okay, so if you want to quickly find out what it does is just compressed sparse row matrix. The compressed matrix will have the indexes related to these entries. For example, this value is located at zeros, column, fourth row, right? Zeros column, 0, 1, 2, 3, and then 1, 1, 9. So all this information, for example, this one is 8th row, fourth column, and all these zeros are not stored. This is more compressed, more efficient matrix. And then we can convert compressed sparse row matrix into non-sparse matrix by using the toArray method. Okay, then we restore our original sparse matrix. There are some other sparse formats available, which can be useful for various problems. CSR, compressed sparse row, CSC, compressed sparse column, so compressed along the column axis, block sparse row, coordinate, COO, DIA, sparse long diagonal, dictionary of keys, list and list. Okay, just take a look at the documentation of sparse matrices, okay, for more details. So another important part of machine learning is about visualization of the data, right? The common tool for this in Python is used by matplotlib library. It is an extremely flexible package. Let's see some of their examples. Since we're using Jupyter notebooks, we can use IPython's convenient built-in magic functions that allows us to visualize graphs inside our Jupyter notebook. So this is one of the magic functions. So don't forget to call this inline, okay? And matplotlib provides this pyplot module, okay, this library, which contains a lot of helpful functions that, okay, allows us to visualize scatter plot, for example, here. So first we generate random data, 500, one dimensional, and another data, also 500, and then just visualize the scatter plot. This is X and this is Y, right? Using the scatter. What about this? So we can also see the images using IAmShow, image show, okay, method. So we create X, Y, and then we generate the data. This is a sinusoidal kind of data, and print the shape of the IM image, which is 100 by 100. So these are kind of sinusoidal patterns along this and this direction. And we can call IAmShow on top of that. So we can visualize images, right? And counter plots, one of the important plots, well, especially when we want to see if the minimum or maximum of your, let's say, objective function, where it is it at the minimum or maximum, right? And or in addition, the matplotlib provides us 3D visualization, okay, like this. So X, Y, and then Z, all of them are available. Okay, so just go to matplotlib gallery to take a look at what other types of visualization you can see. Okay, these are bar plots and histogram, for example, image, contour maps, for example, with arrows, and this type of polar charts, colors. It's a very, very rich library. So I highly recommend you to learn more about this matplotlib library. Okay, there are some other libraries available that builds on top of matplotlib, such as Seaborn. I think import Seaborn as SNS. Okay, the Seaborn is also a very useful library. Okay, let's see. Box plot, category plot, and some other.